All right, so tonight what we were going to be talking about is electron configuration. And what it does is it basically takes the energy diagram that we've learned about previously and it puts it into a more condensed version. And with this, you don't need the energy diagram in front of you anymore. You can just use the periodic table and you'll be able to tell me the electron configuration fully without ever having to have memorized that energy diagram in the order. So what is an electron configuration? Basically, it's just a shortened version of an energy diagram. And so what we're going to try to do is arsenic first. And so this is how it translates. So arsenic has 33 electrons. So what we're going to do is it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. So notice once again, because of Hund's rule, I do not fill in those, I do not partner up those electrons in the highest energy level without, before I had them individually. So I didn't partner them. I didn't need to partner them up at all. So the next thing that we're going to do is try to make this into an electron configuration. So working from the bottom on up, you just write down the energy level, which is 1, then the sublevel, which is 2, or S, and then you're going to write down however many electrons you have in that exact energy level sublevel, and that would be 2. You write them as a superscript. Then the next one would be 2s2, then 2p, and there are 6 in that guy, 3s2, 3p6, 4s2, then we go to 3d, there are 10 in that one, and 4p, and there's only 3 electrons in the 4p, so I'm going to write 4p3. And then to check this, to make sure that I got all the electrons accounted for, all you need to do is add up all those superscripts, and you should get to your total number of electrons, which is 33. Now let's try S minus 2. This is a little different because it tells you that there are 16 electrons for neutral S, but this one has a minus 2. So instead of 16 electrons, I'm going to actually be adding 2 electrons because that negative 2 means you gain 2 electrons. So you have a total of 18 electrons I need to account for. So the way you do this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So to translate this into the correct electron configuration, we do 1s2, 2s2, 2p6, 3s2, 3p6. Okay? So let's try to do this with just looking at the periodic table. So what you guys need to do is get out 4 coloring things, pencils, crayons, whatever, and you're going to need to outline like I do. Okay? So this guy right here is going to be S. So my blue guy is S. Okay, and then the next one, I'm going to do this guy right here. This whole block is going to be the P block. So every electron found in that group is going to have that P shape, the peanut shape. Oh, I want to make that a different color. So this guy, these transition metals, they are all going to be D. They're going to take on that D shape, and all the inner transition metals will take on the F shape. So any electron found in this area down at the bottom would be having that F or the flowery shape. Next thing you want to do is label all of your energy levels. So the first one, the S's, start with 1. So it's 1, 2, 3, 4, 5, 6, 7. And then your second energy level, which is P, starts with 2. So this would be 2, 3, 4, 5, 6, 7. Your D's, because it's the third one you'd run into, is 3. So 3, 4, 5, 6. And then your last group is going to be your fourth one, which is F, and it's going to start with 4. So 4 and 5. All right, so then what you're going to do is you're going to need to count however many electrons are found in that column. So this would be 1, 2 for the P's, or I mean the S's. For the P's, it'd be 1, 2, 3, 4, 5, 6. For the D's, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then for the F's, it goes all the way from 1 through 14. All right, so let's just do a practice problem. I'm going to try to do technetium for you guys. Okay, so technetium is right here. So how you do it, how you fill out the electron configuration for technetium is you start at the upper left, just like we're reading a book, and you start working your way from left to right, top to bottom. So the first one we do is we read the energy level, which is 1, and then what type of sublevel, which is S. And then in that we have accounted for the 2, so that'd be 1s2. Now we're done with this row, so now we're going to go to the next row. This would be 2, and then when you run into the S, so S2. Then you go across. Now we're running into the 2. This is P, so 6. Then we go 3S2 across, 3P6, then 4S2. Now notice we're getting to the 3s. We go 3D, so it goes 3D10, and then 4P6, 5S2. And then it goes 4, and then we've got 4D, and then it's 1, 2, 3, 4, 5, or it looks like that, 5. So it's 4D5. And that's our electron configuration for that one. Let's try for oxygen, a little bit shorter. So then we go 1S2, 2S2, and then 2P, and that would be 4. So for oxygen, it would be 1s2, 2s2, 2p4 for its full electron configuration. Now there are 2 exceptional columns, and those are with your D group, and what happens with them, for whatever reason, it actually is less energy to borrow from the S group, the last energy level of S, and donate that electron to the D. So instead of saying 4s2 3d4, what happens is they take away one of those S's and it's donated to that D, so it's 4s1 3d5. Okay, so same with copper. What happens with that one is instead of 4s2 3d9, it actually borrows 1, so it becomes 4s1 3d10. Okay, this is kind of like a memorization exceptional thing. So what I want you guys to do, and it's these guys, what I want you guys to do is I want you guys to, on your columns, in your colored periodic table that you just did, box out this and box out this guy, do a better job than I just did, and label it as blank S1 blank D10 and blank S1 blank D5. And so what that blank means is whatever row you're on. So if this is 4 and 3, you'd say 4, if I'm doing chromium, it would be 4s1 3d5. Or if I was on molybdenum, this would be 5 and this would be 4, so it would be 5s1 4d5. Okay, same thing with the copper column. You just fill in whatever energy level you're on for that one. And it's only for the last one. So if I got all the way to, let's say, molybdenum, my previous row would still read 4s2 3d10 because I used all of those electrons anyways. So what can you learn from knowing the electron configuration? Well, what you can do is you can figure out how much energy a particular electron actually has, such as based off of where its energy level is and what sublevel it's a part of. The other thing is you can figure out how many valence electrons a particular element has, because the valence electrons are always based off the highest occupied energy levels, which is always your S and P. And from that, you can actually base or figure out the probable charge of that element, which is based off of not the number of electrons, but the number of valence electrons. So when we look at this electron configuration that's given below, and I'm trying to figure out how many valence electrons I have, what I'm going to do is I'm going to look for the highest energy level. So I've got 1, 2, 2, 3, 3, 4, 3, 4. Ooh, so that 3 is not going to be a count because it's not the highest energy level. It may have more energy, but it's not a part of that energy level. So now we're going to be looking at the highest energy levels to figure out my valence electrons. So it would be 2 plus 5, so I would have 7 valence electrons. Now, knowing what we know from the periodic table unit, if I have 7 valence electrons, I want to get 8 or 0, so I'm going to choose to make 8, so I'm going to gain 1 more valence electron, so I would have a -1 charge for that guy. All right, charges. As we've already talked about from the previous problem, when we have S minus 2, that normally it has 16 electrons. But that -2 makes it have 18. And so when you're doing the electron configuration, you're actually going to be doing the electron configuration for argon and not for S or sulfur. You can't tell the difference when we write out the full electron configuration, whether it's for argon or something with a charge that made it to have that 18 electrons. Then we've got the abbreviated or condensed electron configuration. So if we're going to try to do gold, I'm going to just try to tell you how it would look normally. I'm going to read it off to you. So starting at the upper left, if you guys follow along on your periodic table, it should go something like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 10, 5p6. Okay, now I'm on that row, so it's down that guy. Okay, so then I've got 6s, and this is one of those weirdo ones. So instead of writing 6s2, it's actually going to be 6s1. But now we need to go down to this guy, which makes it 4f14, because notice it goes from 56 to 72. Well, where's that big branch or breach of the numbers? And that's right here, so you kind of insert it. So that's 6s1, 4f14, and then it goes back up to 5d10. So that's pretty lengthy. Now, sometimes scientists are like, oh my gosh, that's way too much. So what we need to do is we need to condense even this version compared to the energy diagram. So what you do is you find your element. Done. Okay, so these are the steps. Next, you need to go up to the previous row, go all the way over, and find the noble gas. So basically, you're going to be going up and over for all of this. Okay, so what is the noble gas for this guy? It'd be xenon. Put that in brackets. Okay. Then do the full electron configuration for only the row that the element is found in. So the only row that it's found in is this 6s row. And by putting xenon in brackets, what we're really doing is saying, hey, everything for xenon and its electrons are accounted for. So then what you want to do is 6s1, 4f14, 5d10. So that's how you do gold. If we wanted to do, let's say, phosphorus. Okay, phosphorus, you'd go up and over, so you'd put neon in brackets, and then you'd do that row, which is 3, so it'd be 3s2, 3p3, and then you'd be done. So definitely like the abbreviated version more than the long one. It's just a lot easier. All right, hopefully you have a kind of an understanding. We'll be practicing more of these in class. Make sure you write down any questions you have so I can answer them. Have a great one.